G'day, let's pick up where we left off in our chemical energetics unit, where today we're going to look at the concepts of lattice energy and what are called Born-Haber cycles. Where a lesson objective, we're going to understand the concept of electron affinity and use Born-Haber cycles to calculate lattice energies. So previously, looking into the concept of chemical energetics, we introduced all sorts of concepts, enthalpy changes, enthalpy cycles, Hess's law, all looking at the differences in energy, the energy changes that can occur in chemical reactions. We're picking up right from there by looking at a specific kind of energy change called lattice energy, which, as you might be able to infer from the title there, relates to our ionic bonding and our ionic lattices. So when you think about an ionic bond, what you've been told for a long time is the idea that you've got positive cation, negative anion, electrostatic force of attraction between opposite charges creates a very strong bond, thus the ionic bond. This arranges itself into a three-dimensional lattice, which gives us our ionic compound. So we've been saying it's a very, very stable, very strong bond, a very stable lattice. We can really explore why that is. So think about what happens when a sodium ion reacts with something like a chloride ion. When you've got a halogen reacting with a group 1 metal, for example. These really spectacular reactions. You can look them up online and see some really spectacular reactions showing lots of energy, lots of heat, lots of sound, lots of light being given off. What this implies is that we got very, very exothermic reactions. So let's get a good old-fashioned enthalpy level diagram. If I draw some axes here, we've got our energy change going up there. We've got our reaction progress going across there. So our exothermic reaction, we're going to start with our reactants having more energy than our products. Reactants, higher energy, that's our ΔH up there. Products down here. This energy is released to the surroundings, so thus our negative ΔH values like so. So we can think about why these lattices are so stable by thinking about going in the reverse direction. And the idea that if we go from the reactants to the products, if we want to get the lattice and then reverse that back into the ions, well, if we've released a lot of energy going in one direction, going back in this opposite direction, going back this way, means that we're going to have to supply. We're going to have a positive ΔH where we supply lots of energy into the system. So as a result, if you've got to supply lots of energy to break something apart, it means that it's going to be pretty stable. Hopefully you agree with me there. So our ionic bond has ions combining to form ionic solids that release a huge amount of energy. Highly exothermic from the opposite charges coming together to form a crystalline lattice. And this energy, when these ions come together, is what we're going to refer to as the lattice energy, which I'll put a definition up for in just a moment. But it all comes back to the idea that bond breaking is always an endothermic process. It always requires energy to break a bond, which makes sense when you think about it. You've got to overcome a force of attraction, so you've got to supply energy to that. Whereas making a bond is always an exothermic process, something that can be summarized in the catchy little gibberish, bendomix, where we have bond breaking is our endothermic process, bond making is the exothermic process. So if we've got the ions, we're going from sodium ions and chloride ions, and we're creating an ionic lattice. That's an exothermic process. We're making, thus the negative ΔH. Whereas if we're breaking that bond, we have a positive ΔH. It's an endothermic. Bond breaking is an endothermic process. So we're going to define the lattice energy like so. Lattice energy, which is ΔH. ΔH is referring to the enthalpy change. The delta sign means change. Got a little plimsoll sign. The plimsoll just meaning it's at standard conditions of the lattice. So the ΔH of the lattice, if you recall, we got all sorts of different enthalpy changes, some of which we're going to reintroduce today. Also introduce some new ones that haven't been introduced before in this series. So what is it? This is how we're defining it. The enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. So in our example of sodium chloride here, we have 1 mole of the ionic compound, so NaCl in the solid, is formed from its gaseous ions. So the sodium ions are gaseous, chloride ions are gaseous, making bonds exothermic, very, very exothermic, as we said just before here. So we have a very large negative ΔH value. Do note there are other ways to consider lattice energy, but this is the definition that we're using where we're talking about the energy when we form, thus the exothermic value. So what do we got here? Large exothermic values of lattice energy shows that the ionic lattice is very stable with respect to its gaseous ions. We got a very large negative value for the lattice energy. If I pop a little, let's keep the color scheme the same. If I put a little lat down there, you can think about standard conditions as well, of course, with the Plimsoll sign. That's a very large value. It requires it's very stable because you're going to take a very large amount of energy to go in that opposite direction, as we keep on saying. With respect to its gaseous ions, because that's what we're putting as the reactants on the left-hand side there. So, the more exothermic, the stronger the ionic bonding in the lattice. So the larger that ΔH value is, or the more negative perhaps, the larger the magnitude of the negative value, it implies the stronger that lattice is, because more energy is given off when the lattice is formed. So as we do, let's look at some trends. Let's look at some data. Let's look at some trends for ΔH lattice, and let's see what it's implying, or what our patterns are. In fact, if you wanted to have a pause and just consider what we're looking at, see if you can find some changes for yourself. See what's changing as you go from left to right, see what's changing as you go from top to bottom, and have a think about what you're actually observing there. Well, let's have a look first of all as we go down the group. So let's look at these oxides. If I get my little pen up here. So we've got oxides of all group 1 metals. So we have lithium, which is a 1+, sodium, which is a 1+, potassium, which is a 1+. So these are all the same charge, but as we're going down the group, what we're doing is we're increasing the ionic radius. So you think as you go down that group, you're adding an extra quantum level each time. If I draw some diagrams, maybe down here. So lithium on the second period, we got 2 quantum levels, whereas sodium on that third period, 1, 2, 3. So if these are all ions, if they're all having the same charge, what we're increasing is we're increasing the radius. So as we increase in size, but as we keep the charge the same, so they're all Li plus, and they're all group 1, they're all +1s, and they're all oxides, so -2. What can we see is occurring with the ΔH of the lattice energy? Well, these are all exothermic values, as we said lattice energy will be from our definition, but the lattice energies are decreasing. So we can think about this. In all of our atoms down here, or rather ions, if I get another one with a potassium with an extra quantum level, the part of the ion that actually has the positive charge is the nucleus, because we just got the negative electrons and shells around it. So the actual positiveness of the ion is coming from the nuclei. That is what is attracting the oxide anion. The positive nucleus with the negative anion is that electrostatic attraction, that ionic bond. But as we get a bigger and bigger ion here, as we get further and further from that nucleus, if you think about the radius there, that electrostatic force of attraction becomes weaker. Therefore, the bond between the corresponding oxide, which isn't changing, oxide's further away from the positive nucleus, therefore it's becoming a weaker force of attraction because electrostatic force of attraction is dependent on distance. So as we go down the group, and we can see this with our 2+ ions, magnesium, calcium, strontium, as we go down, as the charge stays the same, but as the ion becomes bigger, we can see that the lattice energy decreases. We can infer that the bigger the atom is, further the positive charge is away from the anion, therefore electrostatic attraction becomes weaker. Therefore, the ionic lattice is becoming less stable. So therefore, lattice energy is going to become lower. We can see a very similar thing down here. This is all just showing the trends again. Same sort of thing, group 1s, but with fluorides, group 2s, but with fluorides, we see that same pattern. It becomes less exothermic, the lattice energy, as we go down the group because the atoms are becoming bigger, or the ions are becoming bigger, perhaps to be a bit more consistent in my vocabulary there. So now the question becomes, what are we changing as we go from the left to the right here? Well, we have our group 1, our +1s there, which we've been looking at. Over here we have our +2s. Over here we have our +3s. Again, we're keeping that oxide the same. So we got something to compare it to. What we observe is that as you increase the charge, the lattice energy is becoming bigger, or it's becoming more exothermic. So we have, if we look at our group 1s, we're sitting in around the -2000s, whereas our group 2s, for our group 2 oxides, they're sitting in the 3000s. By the time we get up to the group 3 oxide, we're sitting in the 15,000s for the exothermic. That's telling us that these lattices are becoming much, much more stable. Remember, the more energy we give off when we form the lattice, the more energy it will take to break that lattice. The more energy to break that lattice, the stronger that lattice will be. So, this makes sense as well. Hopefully, if you think about moving across the period, we're keeping the size relatively the same. What we're changing this time is the charge. The higher the charge, the stronger the electrostatic force of attraction. Therefore, the stronger our lattice is going to be. And we see a very similar trend for our fluorides this time. If we keep the fluoride the same, we look at our group 1 fluoride sitting around that 1000, -1000, group 2 -2500, group 3 up in -5000. So as we increase the size but keep the charge the same, lattice energy decreases, becomes less exothermic. As we keep the size the same but increase the charge of the ions, the lattice energy becomes more exothermic. But there's always a but in there. It is impossible to determine the lattice energy by a single direct experiment. We need to create a specific energy cycle. This is all based on the idea of Hess's law. We said that Hess's law, the total enthalpy change during a chemical reaction is the same whether the reaction is made in one step or multiple steps. So it was that idea of finding the direct route and finding the indirect route. So we can't find the lattice energies, we just got to make an enthalpy cycle. And we've got to make a very specific kind of enthalpy cycle, which has this name Born-Haber, a Born-Haber cycle, which, as you can probably imply, named after two scientists, both German, one called Max Born, another we're somewhat familiar with, Fritz Haber, interesting fellow. I won't go into him here, I think I have before. And this was developed in 1919. So let's build this let's build this enthalpy cycle, this Born-Haber cycle for the lattice energy. Here's what we define the lattice energy as. We defined it as getting 1 mole of our gaseous ions and the energy released when we have the formation of 1 mole of our ionic compound, understanding conditions if we're doing our plimsolls. I don't have plimsolls there, but you get the idea. So we've got the ions in the gaseous state to the ionic compound. That's what we're trying to work out. We can get the standard enthalpy of formation for sodium chloride. So this is something that can be measured. And if we recall our standard enthalpy of formation, it was taking the elements in their standard form and the energy released when we form, thus the enthalpy of formation, form our product there. So we've got sodium metal in the standard state, sodium with its metallic bonding. Chlorine is a diatomic molecule, and we make 1 mole of our formation. So we've got NaS solid plus half CO2 gas goes to NaCl. So then to finish our enthalpy cycle, as you can probably see, we have to go from the elements in their standard states to the ions in their gaseous states. So then from here, if we know both of these enthalpy changes, we can pop our direct and our indirect routes onto our enthalpy cycle, and using our Hess's law, the idea that the energy change during a chemical reaction is the same, no matter how many steps you do it in, we can say that the ΔH of formation, which is our direct route, is going to be equal to our lattice energy plus our enthalpy change for this process here, which is our indirect route going around there. So if we want to calculate the lattice energy, which is the idea of doing this whole business, we can simply rearrange that to say the ΔH of the lattice energy is equal to the ΔH formation minus the enthalpy change to go there. ΔH formation is something we've looked at before, and they're values that can be easily found. The question becomes, how do we get the enthalpy changes from elements in their standard states to the ions in their gaseous state. And this is where a little bit more complexity comes into it, because there's a number of steps involved as opposed to it just being one step. It's a number of steps that we have to do to go from, standard state, from a sodium, I might draw this over here, to go from a sodium in the standard state, which is a solid, and if we got to somehow transfer that into a gaseous ion, or in the case of our chlorine, going from the chlorine in the gaseous state, number of steps, I'm just doing multiple arrows there to show it's a number of steps, to the chlorine ion in the gaseous state, that's where the number of steps come involved. So the process is a little bit different if we're forming a cation or an anion, because, well, a cation is formed by losing electrons, an anion is formed by gaining electrons. So there's going to be a slight difference in those two processes there. Let's look at them. Let's look at the cations first of all. First, we need to convert the elements into individual atoms. And luckily there's an enthalpy change we've investigated previously, which is called the enthalpy change of atomization, the ΔHat to represent atomization. Enthalpy change when 1 mole of a gaseous atom is formed from its element under standard conditions. So we're going to have a ΔH of atomization for our metal into a gaseous atom. Then we've got to convert the atom into the ion, which is also something we've looked at before. It is, of course, the ionization energy, the enthalpy change to remove 1 mole of electrons from 1 mole of atoms of an element in the gaseous state to form 1 mole of gaseous ions. So that's what we've done here. First, atomize, go from the element to the atom, and then ionize, go from the atom to the ion. Like that. So we've got to do those two steps for the cation, and then we've got to do something similar for the anion. Well, we've got to do the enthalpy change of atomization again. We've got to convert our non-metal into the atoms. So the enthalpy change of atomization, these are always positive. Energy is needed to break the bond. Go back to good old-fashioned bendomex. Bond breaking is endothermic. So when we're atomizing a metal, we are breaking metallic bonds. When we're atomizing a non-metal, a molecule, we are breaking covalent bonds. So that's always going to be a positive ΔH, always an endothermic process. But unlike our metals that form cations, our non-metals form anions. So this is where we get into something that hasn't been covered before. And this is the idea of electron affinity, which luckily is just what it sounds like. The affinity something will have for an electron, the same way that you use affinity in your everyday vocabulary to mean liking something. If two people have an affinity for each other, they like each other. So it's how much the atom likes to get the electron affinity. And you can sort of think of this as being the inverse of ionization energy. Ionization energy is the energy to lose an electron to make a cation. Electron affinity, the energy to gain an electron to form an anion. So let's define it as such. The enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of gaseous ions, which for our chlorine, we have our gaseous atom and we're gaining an electron. And in fact, our ionization energy, we should really have plus an electron there as well, shouldn't we? To make it much more correct. So yeah, it's sort of the inverse of these. And conservation of mass, the electron that the sodium is losing, this is the electron that the chlorine is going to gain. So these 4 steps together, this becomes that ΔH1 on that previous enthalpy cycle, which I'll pop back up here. So these number of steps all have to be done to go from elements in their standard states to the ions in their gaseous state. Let's start to put it together by first considering our electron affinity, which is something we haven't looked at yet. It's the energy change, the enthalpy change that occurs when a gaseous non-metal accepts an electron. And there's some good general rules. We like some general rules in our chemistry. The first is that the first electron affinity is always going to be an exothermic value, whereas successive electron affinities, if they've got to gain more than one electron, the successive ones are always going to be endothermic. And what you might want to do is have a pause and see if you can rationalize why. Why are both of these things the case? If you want to pause and then resume now. Well, if we go back to the good old-fashioned Bohr electron model, which I might go over here and get some diagrams going. So we got the nucleus. Nucleus, I'm sure I don't have to tell you, is positively charged. And then we have numerous, I wonder if I can get a circle going. Oh, look at that. We've got our quantum levels going around, all identical, which is much more than I can say for my diagram there. Positive and negative attract each other. Positive, positive, negative, negative repel each other. How much of chemistry do we explain with that simple idea? So if we think about a atom, a non-metal atom wanting to gain electrons, well, as the electron is moving towards the nucleus, it becomes more stabilized. This is an idea we introduced right at the beginning of our video series, the idea that the closer the electron is to the positive charge, the more stable it is. Very analogous to what we've been looking with our ionic lattices. So as the electron moves between quantum levels, it's giving off energy. It's going into a lower energy state. And this is why our first electron affinities are always a exothermic, or generally, maybe I'll say generally to cover myself a little bit there. But these are giving off energy. These are given off energy as they move down through the successive energy levels, through the quantum levels. But when we think about the successive electron affinities, so the same way that we could have successive ionization energies where it loses more than one electron, we can have successive electron affinities if they have to gain more than electrons. You think about an ion with a 2 negative or a 3 negative charge, right? Well, it goes back to our good old-fashioned idea of electrostatic attraction and repulsion. So now let's say that we form the ion, and this ion is now an anion. It's got more electrons, it's gained an electron, it's now got a negative charge. If this has a successive electron affinity, so if there's another electron that's going to be gained, well, boy, oh boy, what have we got here? We've got negative charges repelling each other. So thus, it has to be endothermic to overcome that repulsion. So in general, our first electron affinities are exothermic because these electrons are entering a neutral atom and they're moving down through successive energy levels. Whereas each successive one, we're now got negative repulsion between the anion and the successive electron that it's gaining. Then, as you add an electron each time, again, generally, successive electron affinities are going to increase in magnitude. You know, you think about then having a 2 minus, and you're adding another electron. You know, each time you've got to overcome more and more of that electrostatic repulsion. So let's look at some values. I got some data here if I pop my screen back up. So the first electron affinity for an oxygen atom. So we've got the gaseous oxygen atom. The energy needed to gain 1 electron is an exothermic value because that is giving off energy as this electron moves down through the energy levels. Whereas to form a 2 minus, oxide 2 minus, the second electron affinity, thus EA2. Again, I don't have any plimsolls here, but you know, consider them at standard conditions if you like. The O minus is now got repulsion, negative, negative repel each other, so then it becomes an endothermic process. And we can see trends in the periodic table as well, which is very useful. And that analogy to ionization energy, or sort of being the inverse to ionization energy, comes in useful here as well, because it's going to be the same factors affecting electron affinity, the same factors that affected ionization energy. You know, how much nuclear charge there is, how much inner shell electrons there are, how far the electron is from the nucleus, so on and so forth. So it's affected by a nuclear charge, number of shells, and shielding from the shell electrons. So here's the trend we observe. As we move across a period, we generally have the electron affinity increasing as we move across here because we're increasing nuclear charge, but we are keeping the number of shells and inner shell electrons the same. Whereas, as you move down, the electron affinity generally decreases because as you move down the group, or you can think about moving up the group, it increases. Going down the group, it decreases because we are changing the number of shells and thus the shielding from the inner shell electrons as well. With all that under our belt, let's finally get into it. Let's build some of these Born-Haber cycles as energy level diagrams. So in fact, what we'll do to start, we'll build it as a enthalpy cycle and we'll build it as an energy level diagram simultaneously so you can understand how they are somewhat interrelated with each other. If you want to pause and have a crack, go for it. Let's have a look. What have we got? Let's redraw this with each of our steps for our sodium chloride example to start off with. So what do we have? We've got our ionic compound, elements in their standard state, and ions in their gaseous state. So let's start with the lattice energy part, which is what we're doing all this for to find. So we have the sodium ions, it's the gaseous, plus chloride ions, also gaseous, forming the sodium chloride solid. So this is what we've defined as the lattice energy, the energy released when making that ionic lattice from elements in their gaseous compounds. Sorry, ions in their gaseous state. Then down here we can have the ΔH formation. So I'm going to make this quite large there because we're going to build, in fact, I might even make it a little bit larger. Why not? Nothing but space here. So this is going to be our ΔH formation. So we've got elements in their standard states, which will be our sodium metal, and then our chlorine diatomic molecule, half, because we just want to make one, we just need one chlorine for our sodium chloride there. So this is going to be our ΔH of formation. Now this here, this is our ΔH1 from that diagram earlier. We now know that's consisting of a whole bunch of different steps. So let's go ahead and let's talk about each of these steps that we have to do. The first thing, let's start with our sodium metal. We've got to atomize our sodium element into an atom. So we want to form from the solid to the sodium gas, and just ignore them. We're not doing anything to the chlorine just at this particular juncture. Let's get some different colors so we don't end up with a big mess. So this is going to be the ΔH of atomization of our sodium. We're going from the element to the atom. Why don't we pop some other labels on these ones as well? This is our ΔH formation of our sodium chloride. This is our ΔH lattice also of our sodium chloride. I might put that underneath. Also of our sodium chloride, right? So where do from here? Let's look at ionizing. So now let's go from the sodium atom to the sodium ion. So we're going to end up with that. We haven't changed our chlorine. I'm sort of going off on a bit of a trajectory here. And we've ionized. So we've also got an electron. This will be the electron that the chlorine eventually accepts to make an anion. So this here, this is going to be our ΔH of our ionization energy, our first ionization energy. We've only got one ionization energy for sodium, or to make the 1+ ion anyway. So it's going to be that enthalpy change there. All right, so we've got our sodium where it needs to be. We've got a sodium ion in the gaseous state. Now we've got to get the chlorine sorted out. So let's do the same thing that we did with the sodium. Let's first put it to an atom. So we're going to have another enthalpy change where we've got the sodium ions remaining unchanged. But what are we doing here? We're atomizing our chlorine from the element into just the atom plus the electron that's still hanging around there. And then the very final step, if I label this the ΔH of atomization of the chlorine, and then our very, very final step is the electron affinity that we've just introduced. So what's happening? The chlorine is gaining the electron that the sodium lost, and we have the ΔH of the electron affinity. The first electron affinity, we only have to worry about one here because we're only gaining one electron to make the chloride ion for that there. Boy, oh boy, we did it. So this is the enthalpy cycle there, only we've got about 4 steps for this particular example to build that like so. But, I mean, apart from that, it's still the same process from here to find your direct, your indirect route, and then to put all of the enthalpy changes together, which isn't the most advanced maths. However, with so many positive and negatives, depending on if it's endothermic or exothermic, it can be, mistakes can happen, you know, if you're not careful with all your details. So let's now dive into that there. But yeah, essentially, we've got a direct route there, don't we? We've got a direct route there. So, as we said earlier on, our ΔH of formation is going to equal the ΔH of this one, which I'm going to summarize all as ΔH1 plus the ΔH lattice, which is that one there. So if we want to rearrange that to calculate our ΔH for our lattice energy, we are going to have ΔH of formation minus ΔH1, where ΔH1 is equal to all of those. So that's it as a enthalpy cycle. Let's now put it into an energy level diagram, and let's start to put some numbers and add it all together. What you can do actually, if you want to pause now and have a go at calculating the lattice energy, now that we've got these values down there, so I've got each of the atomizations of our elements, formation of sodium chloride, electron affinity, and the ionization energy for our ions. If you want to have a go at adding that up, that would be a good idea, and then you can check it in a moment. But let's consider what an energy level diagram would look like for this whole process. So we can start with, you know, our lowest energy, our real stable ionic lattice. So we can form the ionic lattice through the ΔH of formation from the elements in their standard form. We can also form the ionic lattice from the lattice energy, from the ions in their gaseous form. And we know that this is going to be a much more exothermic process than that is. So the whole point of this, not to forget, is that's the value that we want to eventually come to, because we can't get that directly. So we can use all of these to build our way around and then use Hess's law to pop a number to lattice energy. So let's go through that process, the same way that we went through that process over here, only using energy levels instead of the cycle this time. So we first atomize the sodium. Well, spoilers, I'm pushing the wrong button. There we go. What am I doing? We first atomize, so going from the sodium element into the sodium ion, and we've got a ΔH for that process, endothermic, so we're going up. Then we can ionize the sodium, so again, ionization energy, that's going to be a endothermic process. Then we can atomize the chlorine, endothermic process, breaking that covalent bond. But then we have the electron affinity, which is actually the exothermic process, as we said just before. So this is where the chlorine is gaining that electron, and we have that overall exothermic release of energy for that to get the lattice energy. Now, with all of these numbers, Hess's law, that route is going to be the same in energy as going around that route. Yeah? Because the energy is conserved. So let's do it. Let's pop all our numbers and see if you ended up with the right value. So we said that the ΔH, if I get my pen back, ΔH of the lattice is equal to the ΔH of formation minus ΔH1, which we're calling all that So let's pop our values, and forgive me for doing so much flicking back and forth between the screen. We have the ΔH of formation, which is going to be minus 411. So negative 411. Oh, you know what, let's move down here because I can just tell space is going to be an issue. Minus 411. And then we're going to minus all of our ΔH1 process. So that involves the atomization of the sodium, which is plus 107. And then we'll add that to the ionization energy of sodium, which is 496. And then we'll add that to the atomization of the chlorine, which is 121. And then we will subtract our electron affinity of the chlorine, which is minus 349. And Hess's law tells us that if we add all of this together, my bracket was annoying me there, which I'll do on Old Faithful, the calculator. Minus 411 minus 107 plus 496 plus 121 minus 349. That gives us a value of minus 786 kilojoules per mole. So our Born-Haber cycle, it's a enthalpy cycle with a few extra steps in there, isn't it? This is what I was saying though, like we're just adding and subtracting numbers, but with so many signs, if you don't have the brackets in the right place, mistakes can definitely happen if you're not popping your attention to detail, not being really careful with that. But as always, show all you're working out. So even if there is a calculation error, you're still going to get your marks throughout the other work that you've done. There you go, ΔH of the lattice minus 786. Final thing that we can have a chat at before finishing up is this idea of ions with uneven charges. Because at this point, we've just been talking about ions that have a +1 and a -1, a sodium plus chloride minus, where we've only got one ionization energy and one electron affinity. But if we've got uneven charges, let's say we have a sodium plus and a O2 minus, so it's Na2O, you know, we've got to make sure that we're taking into account, if we've got to do more than one enthalpy change, that these are accounted for. So let's finish with an example looking at this. Let's consider calcium chloride, where we're forming a chloride single minus ion, but we have a Ca2 plus ion. So I've made a Born-Haber cycle in the energy level diagram of this process there. What you can do, pause, compare this to the previous one. What has changed? What has been added? How are they different? And I'm going to tell you right now when you resume. The first thing is we have two ionization energies for calcium. We have the first ionization energy, so we're going from the calcium Ca plus E minus, so we have the first ionization energy, but then we have a second ionization energy because we have to make a Ca2 plus ion like that. So we have to incorporate two ionization energies, which is what we see here. We see ionization energy 1, and then we see ionization energy 2. So both of those have to be included. And then as a result of this, because our stoichiometry of CaCl2 requires 2 chlorines, whereas our NaCl only required 1 chlorine, we've got to make sure that's accounted for as well. So the stoichiometry requires 2 chloride ions, so the enthalpy chains of atomization and electron affinity need to be multiplied by 2, because you have to do that twice. So where we only had 1 over here, atomization, electron affinity, because we only needed 1 chloride ion, this time we need 2 chloride ions, so we have 2 of them there. So you've got to make sure that you've got all these steps accounted for if you have uneven charges. Similarly, with the ionization energy, if you're making a 2- ion, for example, you've got to make sure, or a 3- ion, you've got to make sure that you've got your extra electron affinities. So if you were making an oxide, you would need to have electron affinity 1 and electron affinity 2. And with that, we finished our first lesson in the second part of chemical energetics, looking at lattice energy and Born-Haber cycles. What have we done? We defined and used the terms enthalpy change of atomization and lattice energy as the change from gas phase ions to the solid lattice. We've defined and used the term first electron affinity, explained the factors affecting the electronic affinities of elements, described and explained the trends in electron affinities of the 16 and group 17 elements. We constructed and used Born-Haber cycles for ionic solids. We carried out calculations with these cycles, and we explained in qualitative terms the effect of ionic charge and of ionic radius on the numerical magnitude of a lattice energy. Here are some tasks you can do if you want to consolidate your understanding. Pause, work through these one column at a time, starting from the bottom and working your way up. Brilliant. Thank you very much. I look forward to next time when we'll continue our look into the second part of our chemical energetics. See you later.